So in this video, we will try to solve a problem using the support vector machine. So we need to draw the hyperplane, so that separates circles from the rectangle shape. So let's say we have different objects. We have 4 objects that characterize circle and another 4 objects that may be that have a rectangular shape. For the moment, let's say these are the two quantities that we measured, length and width, and these are the numbers that we obtain. Okay, before we solving this problem, if you remember in the previous one of the previous video, I explained something about something called as the hyperplane, and the equation of that hyperplane is wtx plus b, and w is nothing but the vector, the right with the right direction. So I need to tell something about the dimension of this w and then the x, how it looks like. So before we solve this type of problem using support vector machine, one point that you should remember is, so I already explained what is R. So R is something related. So R power n means we are dealing with n dimensional space. So we're dealing with n dimensional space. If it's R power 2 means we're dealing with 2 dimensional space. 2 dimensional space, or in other words, we have 2 futures. 2 futures. For example, in this example problem that we are going to solve, we have 2 features, isn't it? That characterize each object. One is length and then the width. So which means, so let's say x is some vector. So which means we have in this case x is equal to x1 and x2. So x1 is one future and x2 is another feature. So it can be length and this can be width. So one, and then what is this w? So if this is a 2-dimensional, isn't it? In this case x1 and x2, they are 2-dimensional. So which means your vector w, that should be, it should have the same dimension as point x. It should be w1 and w2. So if in case if you measured, say we measured for example here object length, weight, width, and also the weight. So which means you have 3 categories. In that case your x will be x1, x2, x3. So this may be length, this may be width, and this may be weight of that object. So in this case the dimension of the w should be exactly same. So w will be equal to w1, w2, w3. So what do I mean by that? So the dimension should be same. And then if you remember in the previous video, I said the equation of the hyperplane is w2x plus b equal to 0. So what does this w2x exactly mean? So w2, so when you take the transpose of this vector w, so let's go back to this 2-dimensional problem, w1 and wt. So if we take a transpose, that will be equal to w1, w2, isn't it? Sorry. So if we take a transpose of w, that will be equal to w1 and w2, and then wt of x, that will be w1 and w2 multiplied by x1 and x2, which is length and the width of each sample. Okay, so this is nothing but w1 x1 plus, this is the dot product of these two vectors, w1 x1 multiplied plus w2 x2. If you look at this, what you see here, so x is a future, x1 and x2 is, x1 is a future, x2 is a future. So what we are doing is w to x is nothing but w1, let's say this is some weight, and w2, let's say this is another weight. So you are multiplying one weight with one future and another weight with another future. So this is something we can call it as w2 wt x. This is just a dot product of w and x, and they are nothing but, we can call it as the weighted So we are adding, multiplying the weight to each feature, and then we are summing it up, isn't it? Yeah. So we can call that as a weighted sum of the futures. So this is something you have to remember. So this is what we are going to do in support vector machine. We are going to find the right direction, which is nothing but a vector. That vector has a dimension which is equal to the dimension of the space, vector space that we are going to deal with. If we have 3 features, that's the dimension of the vector will be. You will have three weights. So we will multiply 3 weights to each of the features. And then finally we will add a bias to that. So that will define the hyperplane. So hyperplane is something related to your actual feature multiplied by weight. So each feature will be multiplied by a weight. That tells something about your hyperplane. So keep these things in the mind, and then let's try to solve this problem. So whenever we are going to solve a problem with support vector machine, something that you have to do, the very first step, you have to identify whether the data here, something here, length versus width, is this data. You have to ask this question: is this data? So we are trying to learn now the or what we are going to do is we are going to implement a support vector machine. So that way you can learn about this algorithm. Okay. So is this data linearly separable? So this is the first question you should ask yourself. Let's see. So what do we mean by data is linearly separable? So what it means is, so let's say if you go back to this problem, so if you have one line, one linear line, say in this case this is your hyperplane, isn't it? If there exists one straight line that put all points of one class on one side and all points on the second class on the other side. So if that line exists, then you can tell that data is linearly separable. So that's the meaning of that. So we have to find whether such a line exists. So you have to, the task is existence. So we are not trying to find that line. First we are trying to know whether that line exists or not. If that line doesn't exist, then you cannot use the SVM technique. So that's something, that's the first thing that you have to answer: is the data linearly separable? So we have to find, the first task is existence, identify the existence of such a linearly separable line. So whether that line exists that can separate category 1 from category 2. So this is the very first question that you have to ask. So for this type of data, you have length and width. So how do you find whether such a line can exist or not? So the one way that you can answer is, you can try to take a difference between length and the width. So you will try to find a mathematical quantity that can tell some story about the whether that helps you to identify the existence of the whether the data is linearly separable or not. Existence of that hyperplane for this type of data. So how do you do that? So let's do this. The easiest, I'm going to call length as x1 for convenience and width as x2. I think this video you will find it a bit more complex when you compare to the previous 2 or 3 videos. So because here we are really dealing with the algorithm of SVM. In using just pen and paper, we don't have a computer. All we are trying to do is solve this problem, so that way you will understand how the support vector machine works. So first thing is we are trying to find whether the data is linearly separable, and how to do that. So let's do some feature inspection. So we have x1 and x2. So let's compute x1 minus x2 for all the points. So for each point, we are going to calculate, for each data point we are going to calculate length minus width. Yeah, so this is what we are going to do at the moment. I calculated already, so I can give the values directly here for the, so for C1 2 minus 2.1, C2 2.2 minus 1.9, C3 1.8 minus 2, C4 2.1 minus 2.2. That's what I did. So, and we have for each data point we have some labels, isn't it? C1 to C4 and then R1 to R4. So let's see. So for C1, the difference between length and width is minus 0.1, C2 0.3, C3 is minus 0.2, and C4 is minus 0.1. Similarly, for rectangle 1, you have 2.3, rectangle 2, 2.5, rectangle 3, 2.8, and rectangle 4, so 2.9. So one thing you can identify from here, so I'm going to put a line here. So these ones belongs to circle, and all these points belongs to rectangle. So one thing we can notice in circle is x1 minus x2. You can see that all the values x1 minus x2 is less than 0.3. Whereas in this case of rectangles, you can see length minus width, so x1 minus x2, or length minus width, this is equal to greater than or equal to, so minimum is 2.3, isn't it? Yes, so 2.3. So here in this case, x1 minus x2 is equal to less than or equal to 0.3. So do you think there exists a gap between these 2 points? Yeah? So it's, in fact, if you look at this point, you have only one column here. Somehow we transposed already by taking the difference length minus width into a one-dimensional problem, more or less. Yeah? So we are nearing the something that we have to do in order to implement the support vector machine. So we already converted some two-dimensional problem into one-dimensional problem. We took length minus width and then we got some number and then we put some mathematical notation. So for the case of circle, this condition applies. For the case of rectangle, x1 minus x2 greater than or equal to 2.3, this condition applies. So this is the step 2. So step 2 is something we are doing some feature inspection. You can call it that way. And now we go to step 3. This is a very important step in the support vector machine. So step 3, check if there is a gap. Check if there is a gap. So this is something already a one-dimensional problem. So this is already a one-dimensional problem. So I will keep this aside and then I will try to plot this one. So if you plot this data, so if you really plot this data in a one-dimensional way, so let's say one point will be minus 0.1, minus 0.2, and then another point is 0.1. Sorry. So what I did is I tried to plot minus 0.2, minus 0.1, and then let's say 0.3 is around here. And then you have one more point, minus 0.1. So you have, it overlaps on this point. So you have already 4 points here. And then you have 2.3, 2.5, 2.8, 2.9. So that may lie somewhere around here. 2.3, 2.5, 2.8, and 2.9. So you have 4 points that belongs to rectangle. So this is x1 minus x2, and these points are x1 minus x2, that corresponds to circles. So what can we say here? So in this case, we can take this point. So this is the maximum in category 1, isn't it? So 0.3, let's call that at D max. And then here 2.3, this is something we can label it as D minimum. So this is minimum in category 2. So D max in category 1, that's equal to 0.3, and I'm just labeling it, yeah, D minimum in category 2, that's equal to 2.3. So the data now comes the rules. Listen to this carefully. So if you can say the data is said to be linearly separable if the following condition exists. So D max, so data can be called as linearly separable if D max from one class, say let's say class 1 or any class you can call, is less than D minimum in the other class. So this is a must. So if this condition exists, then we can safely say the data is linearly separable. So why this condition is a must? So for example, if you imagine say D max in class 1 is greater than D minimum in class 2. So this is not a linearly separable. So how this condition will look like in a one-dimensional graph? So let's say these points belong to category. So all these blue points belongs to category 1. So in this case, this will be the D max that belongs to category 1. And let's say you have calculated x1 minus x2 for the category 2, and then let's try to plot. Let's say those points say somewhere around here on this one-dimensional graph. So in this case, D minimum in category 2. So this will be the D minimum in category 2. So what you see here, so your D max is somewhere around here. So if D max of class 1, if this is greater than D minimum of class 2, you see already a lot of overlap in this data, isn't it? So you don't know whether this point, this point, this point, and this point, and this point, whether they belong to category 1 or 2. So they come in between, isn't it? So this type of data is not linearly separable. So you cannot put a line here and say that everything, all the other point that belongs to, all the points that lie to the right side of this line belongs to category 2, all the point that belongs to left side of this line belongs to category 2, category 1. This is something we cannot do. Or if we can put a point somewhere around here, and still we cannot say everything, all the point that belongs to left side of this point belongs to category 1, and all the point that belongs to that lie on the right side of this point belongs to category 2. So this is not possible. So that's why if this condition is not met, D max from one class is less than D minimum of the other class, then the data is said to be linearly separable. So this is a must condition. So you have to, if you're going to implement the support vector meshing, you have to do some feature inspection and identify whether this condition exists. If this condition exists, yes, then this data, so this data that we are trying to solve, or that we are going to treat this as an example problem, so this data is linearly separable. So this is what we identified until this point. So step 3 is complete, and we also checked clearly, we also identified there is a gap between these 2 points, which means this, and we also showed that this data is linearly separable. And so far all good. And there is one more buzzword that you have to, or maybe in the language of mathematics, this type of data, so something like so you have d max, no, d max from one class is less than d minimum in the other class. This type of and this is true. That's because let's say we can put a point. We can put a point anywhere between these 2 points, isn't it? Between d max from class 1 and d minimum from class 2. That point, let's say C. Let's call that point as C. In this case, this point C must be greater than 0.3 and less than 2.3. So which means this point can lie in between 0.3 to 2.3. So this is something they call it as an non-empty interval. Yeah? So there is a clear gap. If there exists a gap, then this is something in the language of mathematics. It's called non-empty interval. That something exists between 0.3 to 2.3, and you can put point anywhere in between. Yeah, so we have to find the right point. I mean the ideal location, yeah, that separates category 1 from category 2. And one more thing that you have to remember in SVM is, for us, only d minimum and d max matters. So in the language of for SVM, only the point d max and d minimum matters. Why that? So only the closest point from each class, no? So in this case 0.3 and 2.3. So these are the closest points from each class. Limit something called as the or tell something about how wide the margin can be. Yeah, so we completely ignore every other points. So it doesn't matter. We really don't care about the distance between any other points. Yeah. So SVM. So whenever we talk about SVM, SVM tried to maximize the distance between the 2 closest points. Yeah? So that belongs to 2 different categories. So that's the whole idea of SVM. So at the moment, this whatever I'm saying, that may looks like really complex, but you have to remember this. Yeah. So whenever you talk about SVM, so let's say maybe I can write it here. So if you have one-dimensional something like here, then the SVM tried to find the hyperplane. Hyperplane will be 0-dimensional, which is just a point, isn't it? Yeah. So SVM tried to find the hyperplane. In this case, will be simply a point. So to identify the point, it will try to find the distance between these 2 closest points, so that each of these points belongs to different categories. Yeah? So one point will belong to category 1 and the other point will belong to category 2. And the separation between category 1 and category 2 is solely dictated by d max and d minimum. Yeah, so only these 2 points is matters, and every other point we completely ignore from the analysis. Yeah, so keep these things in the mind. So for the moment, let's imagine this looks like some data projected onto some vector, isn't it? It's already a one-dimensional problem for the moment. So we already took some data So it looks like a two-dimensional data, and then we try to take length minus width. Yep. And then I try to plot it. That may look something like here. So it already, to me, it looks like a one-dimensional problem. And we try to calculate something called as D max. We try to calculate something as a D minimum. So D minimum for class 2, D max for class 1. And then we try to check is whether this data is linearly separable. And for that, to answer that question, we have to make sure the D max from one class should be less than the D minimum of the other class. And we make sure that D max from class 1, which belongs to circle, is indeed less than the D minimum of the rectangles. Yeah, so that's something we already identified. So now we can find the midpoint. Yeah? So midpoint is somewhere between 0.3 and 2.3, isn't it? Yeah? So how to find that midpoint? So since we do not have a computer, we are trying to find some easy way to get that equation of hyperplane, which is w2x plus b equal to 0. So this is the equation of the hyperplane. We are trying to find the line that best separates the category 1 from category 2, and since we do not have computer, we are trying to find what this vector will be, w. Yeah, and then we will transpose that vector, multiply it to x plus add some bias, equal to and then we set it to 0. So that should make the hyperplane. Yeah, hyperplane is what? So this is a two-dimensional data, isn't it? Yeah? So if you plot something, you may get some points, and then you have to find a hyperplane that separates circles from the rectangle. So that's what you're trying to do without using a computer. So we did some feature inspection, length minus width. That maybe looks like for the moment it looks like we converted the two-dimensional problem into one-dimensional problem, and then we find the D max in category 1, D minimum in category 2. So now take this midpoint. You know? So let's assume this is the hyperplane for this type of data. So this point, let's say C, this will be equal to what? 0.3 plus 2.3 divided by 2. That should give the midpoint in this line, isn't it? Yeah. So C will be, so C will be equal to 0.3 plus 2.3 by 2. That will be equal to 1.3. So the distance between these 2 points, 0.3 and 2.3, that will be equal to 1.3. So let's write that one. So this is a x. So each point here is nothing but x1 minus x2, isn't it? Yeah. So now we are dealing with one-dimensional space, or r raised to the power 1. So which means each point represent one feature, and that one feature is nothing but x1 minus x2. So let's write that again here in a fresh paper. So x1 minus x2 is equal to 1.3. So this is so if this is if you are going to treat the data as a one-dimensional problem, that this point C, which is equal to 1.3, so that's nothing but x1 minus x2, isn't it? Yeah? It's 1 point. So this is a point with the meaning. What's the meaning of this point 1.3? The meaning of that point is x1 minus x2 is equal to 1.3. So this is what I explained before, isn't it? Vector is a point in a vector space with a meaning. You know, so this is a one-dimensional space. So 1.3 has a meaning. The meaning of that is this number represents x1 minus x2. You know, so which is also the midpoint. And since it's a midpoint that separates these two categories, so this point should be also the hyperplane, isn't it? Yeah, hyperplane for this data, for this one-dimensional data. So this is nothing but a hyperplane. So you have to write this equation in the form of a hyperplane equation, which is nothing but w2x plus b equal to 0, or in other words w1 x1 minus w2 x2 plus b is equal to 0. What? So how to do that? So if you remember, I already explained the equation of hyperplane is w2x plus b is equal to 0, isn't it? Yeah. So if you have two futures, x is equal to x1 x2, then w has the same dimension w1 and w2. So that's what I did. Yeah, so you have x1 and x2, and then if you take the transpose of w, so that will w transpose will be w1 w2 multiplied by x1 x2. So it will be w1 x1 plus w2 x2. So this is nothing but wtx, isn't it? Yeah, plus b. So that's the equation of hyperplane. And if you look at this, our equation looks like that, isn't it? Yeah, if you go back to here, x1 minus x2 is equal to 1.3. So we have x1 so minus x2 equal to 1.3. So we can write this in the form of hyperplane. Since we don't have a computer, we are trying to find the w, w and the equation of the hyperplane. So x1 minus x2 minus 1.3, that should be equal to 0. So what does that mean? So now this means b, if you compare, let's say this is equation 2 and equation of hyperplane is equation 1. So if you compare 1 and 2, it's clear that b is equal to minus 1.3, isn't it? Yeah, approximately 1.3. And so what should be the weight of w and what should be the weight of w2, so that this equation holds true? Yeah, so if you multiply x1 by 1, so that will make x1, isn't it? Yeah, so w1 should be 1. So that way, if the weight of w1 is equal to 1, then 1 multiplied by x1 will be x1, and then what value you should get for w2? Yeah, so what should be the corresponding value? That if you multiply with x2, that should give you minus x2. Yeah? So if your w2, if the weight of w2 is minus 1, if you multiply it with x2, that should give you minus x2, isn't it? Yeah? So which means w2 will be equal to minus 1. Yeah? So minus 1 multiplied by x2, that will give you minus x2. Yeah? So this is the equation of hyperplane. So you have to make sure, find the right w1 and w2 plus your bias 1.3. You have to find w1 and w2, so that way we will get this equation as the equation of the hyperplane. So what's that? w1 is equal to 1. So w2, if weight is equal to minus 1, then we will get 1 multiplied by x1 plus minus 1 multiplied by x2 plus b, that's equal to 0. So x1 minus x2 plus b is minus 1.3, that will be equal to 0. So the equation of a hyperplane is this one, x1 minus x2 minus 1.3 equal to 0, and the vector, possibly the vector, because what we identified is this is something already separating the data once to one side and other side, isn't it? Yeah. So possibly that vector will be w is equal to 1 comma minus 1. Yeah. So the equation of hyperplane w2x plus b, that's nothing but 1 multiplied by x1 plus minus 1 multiplied by x2 plus b, that's equal to 0. We already identified b is equal to minus 1.3. So we almost identified the equation of the hyperplane. So this should be the equation of the hyperplane. So we try to identify the ideal vector. This may be the right direction, but if you use computer, you may find a better one. So this may be the right direction that clearly separates, linearly separates the data, so that you can see category 1 on the left side, category 1 on the left side, and category 2 on the right side. With C, this tells something about your bias, isn't it? Yeah. So this 1.3 is nothing but this B value, isn't it? Yeah. So x1 minus x2 is equal to 1.3. That's the distance between length minus width, and we try to convert that equation into equation of our hyperplane. Yeah. So now somehow we obtain the equation of hyperplane x1 wtx plus b, and we identify the vector is 1 and minus 1. If your vector is equal to 1 and minus 1, weight 1 is 1, weight 2 is minus 1, then we get the following expression that satisfy this condition. So this is nothing but the equation of hyperplane. Okay. So I can prove this equation, which is here. So with this vector 1 minus 1, so this one is the equation of the hyperplane. So this is a one-dimensional, so this is something like, you will see a line. I can show this is the hyperplane that separates this data. So if I plot this data on a two-dimensional graph, and then I can show that this equation, which is here, which we identified, somehow we managed to calculate this vector 1 and minus 1. So this is weight 1 and weight 2. Weight 1 is 1, weight 2 is minus 1. I can show that this could be the right hyperplane for this type of problem. Yeah? So what we did is we just took length minus width, and from there we try to calculate d max and d minimum for each of these categories, and then we showed that this data is linearly separable by showing that this condition exists for this data. D max of one class is less than the d minimum of the other class. So this is something we identified, which also proves that this data is linearly separable. And from there on, we went to get some we obtain this equation, isn't it? X1 minus x2 is equal to 1.3, and we compared it with the equation of the hyperplane, which is wtx plus b equal to 0, and then we know that this is not minus, this should be plus. So this is the equation of the hyperplane, so which is nothing but the weighted sum of each of your features. Weight 1 multiplied by feature 1 plus weight 2 multiplied by feature 2 plus b. That's nothing but your equation of your hyperplane. And then if this is your equation of hyperplane, and if this following condition exists for your data, and this equation clearly separates one category from other category, which we confirmed by testing this condition, d max from class 1 is less than d minimum of other class. And then we also got the difference between this one. So x1 minus x2 is equal to 1.3. This is something we identified. And note that in support vector machines, I said multiple times already, only these 2 points, where is that? I don't know where I kept. So only these 2 points matters. Only these 2 points, the two closest points between that gap, only these 2 points matters. So that's what is going to dictate this number 1.3. So we take the midpoint. So this point is nothing but x1 minus x2, isn't it? This entire line talks about x1 minus x2. So this particular point, which is the midpoint, 1.3. So this is a vector that has a meaning, and the meaning is 1.3 is equal to x1 minus x2. And surprisingly, that looks like your hyperplane. So if you compare the hyperplane equation with x1 minus x2, we can write this equation in the form of hyperplane. I just pulled this one to the left side, and then I tried to identify W and W2 that make sure, so you should find the corresponding W1 and W2 that ensures x1 minus x2 is equal to 1.3. So which is in a one-dimensional space, which is x1 minus x2, that's a one-dimensional space. This particular point 1.3, which is 0 dimensions, clearly separates category 1 from category 2. So this is the 0-dimensional hyperplane that separates category 1 from category 2. And each point has a meaning. Each point on this line has a meaning. So this point means x1 minus x2 is equal to 2.3. This point means x1 minus x2 is equal to 1.3. And this point is exactly the hyperplane that separates two categories. If you remember in the first video, I said if you have a one-dimensional space, your hyperplane will be 0-dimensional. But so based on that, somehow we managed to get an equation that may look like a hyperplane. And then we found that if W1 is equal to 1, W2 is equal to minus 1. If you multiply that with the corresponding x1 and x2, you get this condition meets x1 minus x2 will be equal to 1.3. So this is the equation of a hyperplane, and I can prove that. So this is the right vector. So W1 equal to 1, W2 equal to minus 1, or in other words, I can prove that W vector 1 comma minus 1. So this is the right direction where you can separate your data into two different categories. So this is the right direction where the separation between D minimum and D max will be maximum. I can prove this one. I will, and then I can also prove that this corresponds to the equation of the hyperplane. So we know that equation of hyperplane is W2x plus B equal to 0, which means W1. So in this case, you have two dimensions. X is equal to x1 and x2, which means W should be equal to W1 and W2. So transpose of WT is W1 W2 multiplied by x1 x2, so which is W1 x1 plus W2 x2 plus the equation of hyperplane. We have to add the bias B equal to 0. So in order to get the equation of hyperplane, so we have x1 which is length, we have x2 which is width, we have some category here, some category here. We need to find this line which is your hyperplane line, so which is nothing but this one. So you have to get the equation of straight line that corresponds to hyperplane. So you have to write this in the form of y is equal to mx plus c, or x1 is equal, or x2 is equal to mx1 plus c. So how do you write that? So w2 x2, that's equal to w1 x1 minus w1 x1 minus b. So this will be the equation of hyperplane for our data. So x2 will be equal to minus w1 by w2 x1 minus b by w2. So we know w1 equal to 1, w2 equal to minus 1, and b equal to minus 1.3. So let's substitute this one in this equation. So x2 will be equal to 1 by minus 1 x1 minus b is equal to minus 1.3 divided by w2 is equal to minus 1. So which means x2 will be equal to, so this is w1 isn't it? Yeah, so minus minus w1 minus 1 by minus 1, that's equal to plus 1, so x1, and then minus minus plus and minus multiplied by minus, that's minus 1.3. So this is your equation of hyperplane. Yeah? So this is exactly, that's why I said this looks like equation of hyperplane, because we forced this equation to be the equation of hyperplane by setting w1 is equal to 1 and w2 is equal to minus 1. So now I can show that this is the equation of hyperplane. Yeah, so maybe I will use an Excel sheet to prove that. So just to follow the video. So in the Excel sheet, I already plotted x1, sorry, I already entered the values of x1 and x2. So this is nothing but the length and width. And if you go back to the camera here, so your equation of your straight line is x2 is equal to x1 minus 1.3. So let's calculate that in the Excel sheet. So x2, this is the hyperplane line. So x2 will be equal to x1 minus 1.3. So which is x1 minus 1.3. Here you have this way, and now we can plot the actual data set. Let's do that. So you have something belongs to this category, another one belongs to another category. Now we can also plot the equation of hyperplane line x2 versus x1. So let's plot that. Select data, add the x1 will be here, and x2 will be the equation of hyperplane, which is this one. Yeah, if you see that, we already showed that your hyperplane, no, it exactly divides your category 1 from category 2, and that's because we already identified the right vector. Yeah? So our vectors are nothing but, so w1 equal to 1 and w2 equal to minus 1. I can plot this if you want. So let's put 0 comma 0. So x is equal to 1, y is equal to minus 1. I can plot the vector here. So that vector will be perpendicular to this line. So let's plot the select data at x. Yeah. So this is the trend line. So this is our vector w. So this is our vector w. Okay, since the scale is not same, okay, I can set it to minus 3.5. So that way this line will look, oh my god. Actually, if you plot this in a graph paper, you will see that this is your hyperplane, equation of your hyperplane, this orange dots. I can make it into a line. So that's your hyperplane that follows this equation here. And this is our vector, isn't it? 1, w1 is 1, w2 is minus 1. So that makes our vector w. I plotted it here. So that vector will be exactly perpendicular to this one. So what does that mean? If you project these two data point, all these data point onto this vector, yeah, so that will look like, that will exactly look like something we did a few minutes ago. So that will look like this one, yeah. So and there will be clear separation between category 1 and category 2, and the midpoint, which is a 0 dimension in this line. So that will be your hyperplane that separate this one, this group from the other group. So everything is dictated by d minimum and d max. So that also d minimum and d max are nothing but your support vector. So this is, we already calculated the hyperplane, and now we can calculate the support vector line. Yeah? So So what do I mean by that? So if you remember, in SVM, 3 lines matters. So x1, x2, you have some category here and you have another category here, and then this is your equation of your, you have a hyperplane, and then there will be one point here and another point here. Yeah, that the 2 point that which lie closest to the gap, that defines the gap. Yeah, so one can be d minimum, other can be d maximum. Yeah, and the distance between d minimum and d max, that's called as margin. And the third two lines which will be parallel to the hyperplane, they are nothing but they will pass through the support vector. So we can show that this line is a support vector. Yeah, so how to show that? So I already said, so your equation for your hyperplane will be w2x plus b equal to 0, and for your for your support vectors will be w2x plus b equal to plus 1 for one category, and w2x plus b equal to minus 1 for another category. So this is for one support vector of one category, and this will be the equation for the support vector for the second category. So this is something we can prove now. So let's say for category 1, so w1 x1 plus w2 x2 plus b equal to 1. So we know w1 is equal to 1 x1 plus minus 1 x2 minus 1.3 equal to 1. So which means, so I am going to write it x2 is equal to, so x2 will be, so x2 will be minus x2, that will be equal to 1 plus 1.3 minus x1. So minus x2 will be equal to 2.3 minus x1, or x2 will be equal to x1 minus 2.3. So this will be one support vector, and another one will be, for another category will be w1 x1 plus w2 x2 plus b equal to minus 1. So this is something we are going to prove this one. So in this case, so again substitute 1 multiplied by x1 plus minus 1 multiplied by x2 plus minus 1.3 equal to minus 1. So minus x2 will be equal to minus 1 plus 1.3 minus x1. So minus x2 will be equal to 0.3 minus x1, or x2 will be equal to x1 minus 0.3. So this will be another support vector. Yeah? And we already have the hyperplane x1 minus x2 equal to 1.3, or x2 will be equal to x1 minus 1.3. So this is something I already plotted. So now I am going to show that this is one support vector and another one is another support vector. Okay, so let's plot this one. So let's calculate this one, first support vector and then the second support vector in the Excel sheet. So I'm going to plot the second support vector. Sorry, let's say the support vector 1, which is x2 is equal to x1 minus 2.3, and another one is x2 is equal to 0.3 minus x1. So let's calculate this one. So x2, this is equal to x1 minus 2.3. Another one, x2 is equal to 0.3 minus x1. Yeah, now we plot x1 and x2. we plot x1 versus x2. I'm going to plot the support vectors. R is equal to x1 is this one versus y, which is nothing but your support vector. Okay, and then add x, and then add the second support vector, which is this one. Something is definitely not correct. Oh, sorry, this should be x1 minus 0.3. So this should be x1 minus 0.3. Yeah, so that's the second support vector. What is the other one? Select data, add. So x is this one. I think I did so this is series 2, this is series 3, series 4, series 2. I'm going to add one more. So what I did is, so this is our vector W and that's our hyperplane. Both should be perpendicular to each other. So the way we plotted it, it looks like they're not perpendicular, but if we plot it in a real graph paper, you will realize that in fact indeed these two lines are perpendicular to each other, and that's our actual data, these blue lines, and we try to plot the hyperplane. So we also derived the equation for the we plotted the hyperplane, which is this shown orange dots with a trend line, and then this yellow dots that corresponds to the supporting hyperplane, or something called as supporting vectors, and the same here on the other side. And then something we can show is we can identify which of these points are the support vectors. So if you remember, so the support vectors, so if you point to be a support vector, it should follow this condition. So x1 plus x2 plus bias, that should be equal to 1, and then another condition is x1 plus x2 plus bias, that should be equal to minus 1 for support vectors. For one of the support vector, it should be plus 1. For another category, that should be equal to minus 1. So let's check that. I mean, like, sorry, this should be multiplied by W1, W2, W1, W2. So W1 multiplied by x1 plus W2 multiplied by x2 plus bias, that should be equal to 1. W1 multiplied by x1 plus W2 x2 plus bias, that should be equal to minus 1. So we can identify which points corresponds to the supporting vectors. So we can try that. So let's do that. So W1, is 1 multiplied by x1 plus W2 is minus 1 multiplied by x2 plus bias is this value, plus bias is minus 1.3. So you have something that's equal to 1 for one category. So which means this point is a support vector. So one should be so for one support vector, wtx plus b, that should be equal to 1. So this is one support vector, and for second support vector wtx multiplied plus b, that should be equal to minus 1. So this should be your second supporting vector. Yeah? So 2.2, 1.9. Yes, so if you go back to the table that we calculated here, if you go back to the table that we calculated here for length and width, so this dictates our boundaries in it, yeah? So which is d max, and then d minimum is 2.3. Yeah, so the point that corresponds to d max should be equal to 2.2 and 1.9. So this become the support vectors. So this become our support vector, and then the d minimum in the category 2 is 2.3. So that corresponds to R1, which is 3.5 and 1.2. So this is something we can this is what we try to prove in the Excel sheet. Yeah, so we see that 2.2 and 1.9, so that becomes minus 1. Yeah, so that becomes one support vector, and another support vector, the equation says that wtx plus b, that should be equal to 1. So that point corresponds to 3.5 and 1.2. So the support vectors are 2.2, 1.9 from category 1, and 3.5 and 1.2 from category 2. So these two are the support vectors. So in the final exam I may give some data, and then I will ask you to identify the support vectors, yeah, in this type of data. So you have to show it correctly, you have to do the calculations correctly. Actually the problem is not that big, since I tried to explain step by step. It took really a lot of time, but once you know the algorithm, you can solve this type of problem in less than 10 minutes. So SVM is really an really easy algorithm. So far what we learned is how the algorithm works, and the take home message is something you have to remember. So the support vector machines, you have to remember only three equations. One is the equation of hyperplane, wtx plus b equal to 0, and then the support vectors, wtx plus b equal to plus 1, wtx plus b equal to minus 1. So these two will be the support vectors, and this is the equation of the hyperplane. And obviously to get the hyperplane, the support vectors, the game that we have to play is somehow we have to identify the vector, the direction of the vector, where the separation between these 2 points that defines the gap will be maximum. Yeah, so that completes our mathematical procedures involved in the support vector machines. Yes. So I mean, without entering into I mean, at the moment we try to learn the whole algorithm using a two-dimensional data. Obviously, if you have a higher dimensional data, this may be very difficult to solve using a pen and paper. But for the moment, we know how the whole algorithm works. Yeah? So from a two-dimensional data, we try to identify the hyperplane, and to get the hyperplane, we played with some of the features by calculating length minus width, and then from here we somehow converted the equation into the expression that looks like a hyperplane, and then we tried to calculate the corresponding vectors w1 and w2 that ensures the separation between two categories. And then we also try to identify b, which is nothing but the distance between the 2 points that defines the gap between the two categories, two closest points that defines the gap between the group 1 and group 2. And then we prove that by solving the problem, we prove that these are the equations which corresponds to the support vector machines. So one equation corresponds to hyperplane, one to the one high support vector, and another equation to the another support vector. So maybe I may give you some problem for like a homework. That's something you can try to solve by yourself, and then maybe in the computer lab we will try to implement this algorithm maybe for data maybe with more number of rows, but we will stick to the two-dimensional data even in the computer lab. Yeah? So that's all for today. Maybe in the next week we will learn something about principal component analysis, and then maybe the following week we will learn about deep neural networks, and if we have time we will learn something about the k nearest neighbor algorithm. So thanks for listening.